Welcome to today's seminar at the Institute of Advanced Research in Artificial Intelligence, IARAI. It is my great pleasure today to welcome Professor Ioannis Giannopoulos. He studied computer science with a focus on artificial intelligence and human-computer interaction at the German Research Center for Artificial Intelligence, the ETH KI, and he's an alumnus of the ETH Zurich, where he was also a lecturer before joining the Technical University of Vienna as a full professor for Geoinformation and IARAI faculty. It's my great pleasure to welcome you, and I look forward to your talk. The floor is yours.
Hello, everyone. Thanks for the nice introduction. I actually studied computer science in the Saarland University, where the ETH KI is also. I will talk about location-based services, something that probably the most of you know what it is. We use it daily. Just a short introduction, what are location-based services? More or less, as the word suggests, you get a service based on your location. This can be as simple as a navigation instruction. From your location, go left or right. You would guess how many people worldwide use any type of location-based services. What would you guess? What we know from statistics in the US, for example, in 2018, we will have the results or the numbers. 242 million people, 73% of the American or US population, are using or were using a location-based service. Just to show you how much this area is growing, in 2013, 5 years before the number I told you, we're just 37% of the total population in the US, 123 million. Location-based services can be as simple, again, as a navigation instruction, but it can be also more complex. And we'll see some of these examples and where machine learning is very important for this and how machine learning can help us understand some of the processes that are involved when we work on the area of location-based services. The work I will present, of course, is not only mine. A lot of people have worked with me, or I have worked with a lot of people. For example, these are some people of my group that are working on this area, spatial machine learning and location-based services, or some parts of it at least. And of course, many colleagues around the planet where we work together over the years on several fields in the area of location-based services. So, if you think of location-based service, why is it so interesting? Why are we working on this area? If you consider the context that is relevant for a location-based service, of course, the environmental context, so the environment we are using this systems or these services. Then we have the technological context, so we need a certain type of device in order to interact with, to get the information we need, to interact with our surroundings and vice versa. And of course, very important, the user context. Who is a user of this LBS? How can we utilize the knowledge we have from the user in order to make the whole experience better, to make the best out of the interaction and the service that we can provide to this user. And of course, machine learning can help us on that. So what we are interested in is to figure out the process to be modeled. So if you think of the application scenario of navigation, for example, we know that there are processes like orientation, self-localization, monitoring, recognition of the destination. We know that there are these processes. We don't know necessarily the order they occur and how often they occur. Machine learning can help us to more or less identify the sequences. When do this process occur and how can we model them? By knowing that, of course, we can do research and figure out other things. So for example, how does wayfinding work? How do people go from A to B? When do they utilize, or when do they apply one process than the other? Of course, there is always a black box behavior, but still, we can answer the research questions with them now. As I told you, there are a lot of different technologies involved when we talk about location-based services. Still, the most popular one is, or are, smartphones. But in research, you will see a bunch of devices like smart watches, smart glasses. Like a couple of years ago, there was quite a big hype with Google Glass. It's more or less a simple glass with a very small prism over your eye, where you more or less can see some information somehow augmented in the reality, in the environment, but not really augmented reality in the sense that you have the visual objects fixed in the environment. You can have data glasses where you have actually sort of holographic experiences like the HoloLenses. And depending on the technology we utilize for the service, the interaction dialogues are different. So how the user can communicate with the system in order to perform an interaction, and how the reactions of the system are. So it's very important to know which type of technology we use What are the interaction dialogues that are possible or available? Auditive displays, visual displays, we have tactile devices, and of course, depending on the type of the device, the data we can collect while someone is interacting or using a location-based service might differ significantly. So we need to inform our models also concerning the type of device. Coming to the user, everything we do is actually quite user-centric. Of course, also humanity-centric, but the user is more or less in the center of everything we do in this type of research. We try more or less to optimize location-based services in order to create better experience for the users. Of course, we need to know the user, we need to have some information about the abilities of the user, the preferences of the user, the knowledge the user has about his environment or her environment, the surroundings. And of course, machine learning can help us obtain this knowledge, information we need to know. Of course, the interplay of all these things, the interplay of the context I mentioned at the beginning is very important, and there are also interactions between them. And of course, as in most of the disciplines, we have finally to evaluate our results, what we get. So what are we interested in? Why is space so important? And how can machine learning help us? So first of all, the space the user interacts in is very relevant to what we're doing. For example, mobility patterns. So what do I mean with the space the user interacts in is more or less the surroundings, the local surroundings of the user. This can be the trajectories of the user and the elements you can obtain or extract from this surrounding. Then the spatial information the user interacts with. This can be the information provided by the LBS system in any form. Can be a visualization, can be auditive. It's also very important to know how the user interacts with this information, and it's relevant in order to learn from the user or learn the user. And finally, we are interested in the space the user interacts with. At the very beginning, the space the user interacts in is more or less everything in the surroundings. Here is more or less the actual elements the user interacts with. This can be building facades or any other amenity or landmark in the surrounding environment. The interesting thing is we have this data, but there are a lot of errors in this data. But still, we can do a lot of things with OpenStreetMap data, for example. You will see some examples later on. And these are the three spatial components we are focusing when we're doing research on RBS. So what are relevant environments? Of course, we need to collect data, a lot of data, in order to be able to, first of all, understand the process, understand the user, understand the needs for a location-based service. And for this, we have to do a lot of experiments in order to collect the data we need. And one of the relevant environments, of course, is the real environment. It's very cumbersome to collect the data you need there. As you can imagine, it can take months, it can take years in order to get a sample size that is sufficient in order to do statistics at least. Right? Then we also collect our data through virtual environments. One of the benefits next to that, you of course can collect data faster because it's easier. You don't have to, let's say, avoid rainy weather. But exactly this is the point where you get also a big difference. In virtual environments, you can control the experiments where you collect your data from ML, which means when you have an experiment in VR, you know that, or you can design it in a way that every participant was running the trials, the tasks, or performing the tasks under the same conditions. In the real environment, you can never know, or it's difficult to control for weather, for example. One day it can be a rainy day and pretty cold, or a sunny day and very warm, can be crowded, more or less traffic. So all these effects can not be controlled in the real environment. We don't know the effect they have on your data. In a virtual environment, we can do it quite well. About a year ago, we managed to go also outdoors in the real environment, but with mixed environments. Like we combine the real and the virtual environment in order to collect the data we need. I will show you later on some technologies we developed in-house in order to be able to do all this stuff. We use a lot of technologies that are out there, like smartphones, smartwatches, VR glasses, and so on. But of course, often these technologies are not enough. On the bottom left and bottom right, you see two colleagues of mine from Zurich. And here we have developed more or combine different hardware components. For example, on the bottom left, you see an eye tracking glass, a mobile eye tracker, and on top of the helmet, you see a smartphone. And we use the smartphone as a low-cost sensor in order to track the head position in space, the location of the user, other variables like accelerometric data, and so on, and fuse this data with the eye tracking data, with the data we collect from this eye tracking glasses. Mostly, we use this technology in order to observe the users while they're performing the task. On the bottom right side, you see my colleague Dominic Bucher, where he is wearing mobile eye tracking glasses combined with a Google Glass, with a small prisma. And this combination, we implemented it in a way that we can more or less interact with our eyes or through our eyes with the mobile device, in this case, Google Glass. So for example, you can look somewhere and something happens, either explicitly or implicitly. So you can ask for information or obtain information through our eyes. Mobile eye tracking or eye tracking in general, is a technology, a sensor that we use very, very often in order to observe the user. Because in order to train our models, let's say in order to optimize the AI under the hub of the LBS, we try to understand how some processes, like cognitive processes, work. We try to understand how the users solve the tasks. And for that, we have, of course, to observe them. We have to observe how they solve this task. Just to give you a very, very small introduction what eye tracking is. So you can use eye tracking once for observation, as I told you, to observe the user, and once for interactions. So you can enable gaze-based interaction, either with the device or with the environment, in order to collect your data. So in the simplest terms, eye tracking is the measurement of eye activity. Where do we look? What do we ignore? When do we blink? How does a pupil react to different stimuli? You have to distinguish two things, two actions. So we can use our eye movements content independently. So how do our eyes or our eye bulb moves in space? These are the eye movements. And the good thing about them is we know from research already from the 60s, from Yardbooks, that these eye movements are task dependent. So we can use them to predict for prediction. So you will see later how one of the examples we did. And then you have also the gaze, so where someone is looking at. For example, someone is looking, I don't know, on a church, on the facade of the church while he's performing a specific task. So I will start with an experiment and show you an example of how we use eye tracking in order to observe users while they're solving one of the typical tasks in our domain. And through this experiment, we try to understand how people perform the task, how people localize themselves in the environment. As I told you, this is one of the processes for navigation, but more or less, when you're using an LBS system, you always have to localize yourself. Otherwise, the location-based service, the information you get from the service doesn't make so much sense because you don't know where you are. I guess many of you now think, but this isn't that a trivial task. You might assume this, but you will see it's not as trivial as it looks at first. This work was done in Zurich with my colleagues there. It's already a couple of years. And what we want to do here is we want to observe the process of self-localization. How do people localize themselves in an environment where they are unfamiliar? So research questions, or some of the questions we were interested in, were to understand more or less what are the differences between successful and less successful participants concerning, for example, the visual attention on map symbols. Were they looking more on map symbols that were also visible from the current location, which is an efficient process if you think it. And of course, we're also looking on the switches. So how often were they looking on the environment and how often the map? So were they looking mostly on, let's say, helpful landmarks, or the ones that you can actually see or not? So how did we do that? So first of all, we had to find people, participants, a lot of them, that were not familiar with this environment. Funny story behind the whole experiment. We managed to make a deal with a youth hostel there in Zurich. And they're calling us during that when they were expecting a bus full of tourists. And we were going there overnight and trying to convince the tourists not to go out during the night and first thing in the morning to come with us and do a crazy experiment. So what we did in the next morning, for the few ones that agreed, we more or less provide them with the instructions. We gave them the technology they had to wear, like a mobile eye tracking device, and very simple touristic map of Zurich. It's more or less the map you can see on the right side of this slide. It's a very simple map where you can see some of the landmarks of the environment highlighted, and a pen. That's all. We were able to move around, and the only task that we asked them to perform was to mark on the map the location where they think they are, to self-localize. Here you see the result. This is at least some part of the result, some clusters I chose. More or less you can see that it's not as trivial as you think. About half of the people managed to solve the task correct. So they, more or less the cluster you see in the middle of the screen. But you had really cases where the people were totally off. So you had cases like this here, so this one is the correct one. But you had people that were somewhere on the left side of the river. So something that you would not think that would happen, again, because we thought that it's a trivial task, but apparently it's not. And what we found out is more or less how the matching process works and what are the differences between successful participants and less successful participants, or participants that didn't finish the task. So as our hypothesis at the beginning was that the successful participants will easily find more or less the correspondence between the map symbols and the elements in the real environment. It was true. And we can identify, so knowing how this process works, we can inform the AI of the LBS in order to recognize this activity on the one side, and then recognize if someone is doing it good or not, and help and assist. For example, through changing the visualization that is provided to the user. So more or less, I understand, or the system understands that the user is now trying to self-localize, but is having troubles. Let's adapt. Adaptation is a good thing, but can cause a lot of problems, which I will tell you later on. Next to the observation method of or next to the observation experiments we perform using the eye tracking technology, we can also enable gaze-based interaction with mobile devices, and later on we'll show you also with the surrounding environment. We can enable gaze-based interaction with mobile devices, and this will help us to understand which information the users of an LBS perceive, for example, as effective or helpful. Where do they look? Where do they search for information? How do they behave? Why are they doing that? And we can inform again the system in the background. By doing that, we can enable explicit and implicit interaction dialogue. So we can optimize the whole life cycle, the cycle of the LBS and interaction with the user. What is explicit interaction? More or less, I'm looking somewhere and I'm expecting a reaction of the system. An implicit interaction is more or less the system is tracking me in the background, so I'm not really doing something special or not expecting to have an interaction with the system, but the system is tracking me, and at some point, for some reason, because of the model that is running on the background, the system decides to adapt. So this happens without me asking directly. Very short about eye movements or gaze-based interaction. So what we do is more or less is we're looking on fixations, saccades, blinks. What are fixations? Fixations occur more or less when our eyes remain relatively still over a period of time in a spatial proximity, which is often in research interpreted as interest. And saccades are more or less the rapid eye movements that happen in between fixations. For the people that work with in the mobility domain, this might sound quite similar to trajectories, right, in 3D space. And this is how we work with them. Very often we use eye movements or the data we collect from eye trackers as a trajectory in 3D space. Just to give you an example how we can use gaze as an implicit interaction method for location-based services, we use the gaze as an input, and the system is always tracking the user, the location of the user, the eyes of the user, what the content the user is looking at, and can use it, for example, later on as an implicit bookmark to support orientation while we are interacting with the location-based service. And of course, similarly, we can also enable explicit interaction, also implicit actually, with the surrounding environment. So we can inform an LBS, we can more or less, next to the context that we mentioned in the beginning, like the environmental, technological, and user context, now what we try with our colleagues is to also enable gaze context in order to inform the LBS. So where is the user looking at? And people in our domain are using machine learning in this direction because for this problem. And one of the reasons is that the eye tracking data in the outer space are not very accurate. We play there with about 1 to 4 degrees of error. in the outer space. And what they do is more or less we train models in order to have a fixation somewhere in space that is, for example, if you see on the image on the right side, you can see that the fourth fixation from the left side is a bit right off the tower. So what you try there is to understand where, I mean, this is not so difficult here, but you have cases where you have high ubiquities. And you try to match the gaze points to the proper element. We have already done that in the past, or we started with this for linear features, and we called it gaze map matching, similar to the vehicle map matching. It works quite well, but it's still a lot of work that we have to do there. The models are not as optimal as we would like them to have. And of course, another example is, since you can do this and you know where the user is looking in the environment, you can inform the LBS and provide the appropriate navigation instructions. So you can use the gaze of the user in order to understand where the user is looking at, and then if the user is looking on the right corner, on the right street, you can inform him, hey, this is the direction you have to take, and avoid more or less, one of the things we want to do is we want to avoid the constant interaction with location-based services. And one of the ways we can do that is through the gaze, by informing the LBS through gaze. And how does it work? More or less, you use an eye tracking device, a routing service, could be any map service. And then we have a model of the surroundings, and we try more or less to match the gaze to the proper street network. And once the user is looking at the street network that he has to cross, then the phone in the pocket can be implemented in a way that whenever you're looking in the right direction, your phone is vibrating. And we tested that. It works quite well. The people do not perform any mistakes. They're fast, and it works very good. The problem we have here is, of course, that you often do not learn your environment, and this is, let's say, the trade-off there. And this is a huge problem, especially if you speak with people from cognitive sciences. What we try now to do is we try to optimize the whole process and provide instructions in the form turn left at the supermarket on the left side. The problem we have there is actually not as trivial. So if you look on a map, you can automatically extract information where a supermarket is, where a restaurant is, and then you have also the street network. Where do you know if from the side you're coming, if you can actually perceive from the facade that this is a supermarket or a shop or whatever? And this is a big problem when you try to automate the whole process and provide automatic instructions for navigation. So how do I know if the information I provide to the user is actually visible or the user can perceive it? So one of the solutions we are working now on in order to solve that, thanks David for the source of Mapillary. So we try now to take the Mapillary data and train an algorithm to understand or to more or less recognize specific semantic entities in the environment. For example, if my algorithm matches some specific intersection points, more or less junctions, and I provide the information shop 1, shop 2, shop 3, the algorithm should recognize automatically, or our model, if a human could actually detect this. And this is what we're doing now in order to solve this problem. Now we'll show you some more concrete examples, my favorites, where we applied machine learning and the problems we have encountered. And one of them are this content adaptation, so gaze-based map adaptation, where we use simply the eye movements of the user for content-independent adaptation. So it means we didn't look on the content that the user was inspecting while performing the tasks. So more or less, we trained a model to be able to understand from the eye movements of the user the activity the user is performing on a cartographic map. So back then in Zurich, we spoke with a lot of people from field of cartography in order to understand, okay, what are the typical map activities that users are performing. And map is quite typical when you work or interact with a location-based service. So one of the things is free exploration. You just look around. Global search, where you're searching something on the map extent. Then you have a focus search, where you look something around your spot, more or less around your actual location. Linear search is when you're inspecting a line feature. In this case, it would be a street. Route selection, so you want to go from A to B, which route, how you design your route. And finally, polygon comparison. Very often you compare polygons like parks, lakes, and so on. What we did, We performed empirical experiments in order to capture the eye movements of the user while they were performing multiple times these activities under controlled conditions. From these captured eye movements, we preprocessed the eye events like fixations, saccades, blinks, and tried to characterize these activities through these features. And we trained our model to recognize activity. And finally, it was used for a map adaptation. Content independence, important thing here. Now think of a user or a GIS analyst, a GIS expert working with a map, and that this person is inspecting a line feature. So the algorithm is able to detect that and adapt automatically in order to support the cognitive process of the user. So more or less, meaning we try to minimize the cognitive load and come faster to result. When you do that, especially when you work with spatial data, we have the problem that I might be inspecting a line feature because I'm searching a point feature, and this is gone now. And also, when you are working with spatial data, you are using anchor points of your surrounding environment as a reference point in order to orient yourself. And by changing the visualization, you might get lost easily. So we need content-dependent adaptation. So the next step we are focusing now is also to integrate the content of the user, what the user was watching at and interact. And of course, the research behind eye tracking, the human behavior research is huge. So we can really get great data like that in order to get something. I mean, this is a very simple example, but you get the idea, right? So the system, the LBS, recognizes that you want to go from A to B and automatically suggests you, provides you a recommendation. All these experiments we do are actually very difficult to control, and it can take years in order to get data sets that you can actually work with, right? And it's very difficult, what you have observed over time, it's very difficult to understand if someone is familiar or not. What does it mean, familiarity with the environment? It's easy to say binary, I have been here or not, I'm familiar or not, but is there a difference if you are working in an environment or in a space for a month or 2 years or 3 months? And why is that important? First of all, for experiments, when you collect the data, we have to ensure that the participants are familiar or unfamiliar. And we have also, it's important to know the familiarity level of the user, because you can more or less balance the information flow between the system, the LBS, and the user by knowing the familiarity level. So for example, I live now for 3 years in Vienna. If the system tells me, okay, the coffee place you're looking for is behind the Karlskirche, I know from anywhere in Vienna where to go. So I just simply need one landmark and I will find it properly, right? I mean, I need also the side of the building, but it would be easy for me to understand this instruction. If you have never been in Vienna, maybe, okay, landmark like a Karlskirche, it's easy to find. But if the system will provide you some type of landmark out behind the church XY, you might get difficulties. So you would need another service, more or less, in order to get there. So depending on the characteristics of the user, we should balance, and can do that actually, the information flow. And what we try to do now, it's a work in progress. We have already some results. We are not happy yet with that. We try to automatically detect if a person is familiar or not with the surrounding environment. We try, of course, always, with the architectures we apply, we train. We want, of course, to automatically detect this, but we are very interested into the why. Why is it working? Or when we know the why, or when we have some hypothesis that we want to evaluate, this might help us also come up with better features. And one of the questions are there meaningful patterns that we can extract and interpret? And how about familiarity level? So more or less what I told you, binary, it's easy, but how about the level? We lack there in theory. It's not about machine learning here, we just don't know what it means. So we're working with cognitive scientists in many of these fields and many of the examples I showed you so far, because human cognition is very important for all this tasks in the area of location-based services. So how do we do it here? More or less, again, we perform controlled experiments. The first one was in a real environment, in a virtual environment, where people were navigating in some parts of the city of Vienna virtually, and we chose places that were familiar or not familiar. And we were tracking like head position, space, mobility patterns, where we're looking at how long they were looking somewhere, elements of their surrounding, as I remember from the first component, the space the user interacts in, more or less for every location point, for every point in space. We tracked also every, let's say, point of interest that was in the surrounding environment. And we applied different models to figure out something meaningful, and we get something, but it's not something that I would like to present now because it's still weak. But we are getting there. Now we are collecting also data from the real environment to calibrate our model. More or less, we are doing the same, but of course in the real environment with different high precision sensors. You will see later on an example of how the users of our experiments run in the city of Vienna. Place research for LBS. So we have a student that is working on classifying the type of area user interacting in or interacting with. Why is this important? Again, it's the environmental context. Depending on the area I'm interacting with an LBS, or I can optimize the whole dialogue between the user and the LBS. So it's important for me to know, or for the system, for the AI in the background to know, okay, what is the area? What are my options here? What can I do? What do I know from the past, right? And what can these areas be? Can be a historic area, can be a touristic area, can be a business area, can be multiple types of areas, right? And what we do is we use available semantic annotations to learn from. We'll show you later on a great data source that helps us a lot over the last 2 years now. It's amazing what you can do with semantics from VGI data, like OpenStreetMaps. So what my student did here is more or less, for every street segment, he more or less extracted all the street segments, and for every street segment, he created a list of semantic information, more or less. If there are points of interest in the left or right side of the street segment, these were not attached to this segment. Then, of course, by extracting specific areas, like where we had ground truth, he trained them all and he got really nice results. So after the environment, of course, once you know the environment you want to test, there's also the question of timing. So we balance information, we know what type of information because of the environment, we know the user, we know what the user was looking at or is looking at. And of course, now the question is, when should we provide the information to the user? How can we mold this? It's about timing, right? So when do you want to receive navigation instructions? And this differs significantly from user to user and from environment or setup to setup. Can we mold this? Yes, we can. We tried it with econometrics. We performed or applied a time-to-event model, urban analysis here. And what you see here on the right side are some curves of users with different characteristics. So, for example, the red line is Alice, age is 22, with low spatial abilities. And for a certain street segment with an intersection at the end, this would be the probability that at the normalized distance, she would have asked for instructions. What we do here, again, how we collect the data from a bunch of experiments we do over I think the first experiment started 2016, and they are actually running still now in the city of Vienna. Actually, at the moment, it is still running, where we have people equipped with a lot of sensors and a buzzer, more or less, and we provide them a system that is not giving them instruction unless they ask for it. And this is more or less how we model this time to event. And it works quite good, actually. We have already one publication where we did that in the virtual environment, and now we are, again, calibrating our model with real data. And of course, we are very much interested into the complexity of decision-making. Everything we're doing, more or less, when you use a navigation system or an LBS, this has to do with decision-making. So we have to make a decision to go left, go right, go straight, go back. And this complexity is strongly coupled with the abilities of the user, the environmental setup, so how does the surrounding environment look like, and the device. So we know that there is a complexity coming from the environment. So for example, something that we know already from the 50s probably is that if I have a three-way intersection, probably it's less cognitive challenging when you have a six-way intersection. So three-way and six-way is more or less three options or six options to take. This is very simple. Of course, it has to do with architecture configuration, has to do with slope, has to do with visibility, and so on. So we know that there is a complexity of the environment. we know that there is a user, the abilities of the user are crucial. So one user needs more information or less information in order to be able to process it and make a decision. And of course, there's always a device in the middle, and the device and the instructions, the complexity of the instructions is also crucial in order to come up with a model. So more or less what we are looking for is to figure out the interaction between these three complexities in the user model. We have come up with some basic models for that, but it needs work. You need to understand the environment. We need models that are good at explaining the complexity of the environment. And with complexity, I mean the cognitive complexity of making a decision. The same holds also for the instructions. What instruction is easy, what instruction can be received as complex, and all this, of course, in an automatic way. So for all these things, how do we get our data? You have realized by now we do a lot of experiments. You can see two of our students, Sophie Hermans on the left side, she's now working on a project where she tries to more or less detect all the elements of the environment, like chairs, benches in the outdoor space, with this head-mounted display. It's a HoloLens, which has also, next to RGB cameras, has also depth sensors. We try to classify, we try to come up with architectures that are good at classifying point clouds in order to detect them independent of the light conditions in indoor spaces. In outdoor spaces, because there is interference with a depth sensor, we will combine image-based classification with depth sensors. And she's doing a lot of experiments now where she's more or less for hours sitting around and looking in the object, different types of objects for hours. It's exhausting and quite boring, but the segmentation process she's doing, everything she's doing in the background is awesome. On the right side, you see Antonia, and more or less you can see the setup of our participants where we collect our data. So you see this helmet, on the top of it, we have a very high precision inertial measurement unit. With this, we can more or less track the head pose in space very accurately in a frequency of 400 Hertz. Then we have an mobile eye tracking device. I should have put the evolution of eye tracking devices. In the beginning, when I started, it was like exoskeleton things, and now they look more like a Ray-Ban glass. You probably would not notice that these are not typical sunglasses. A high precision GNSS sensor to track the location of the user and track the trajectory of the user. A clicker, for example, when we do the experiments with timing, where we try to understand when does someone need instructions. And of course, we come up with a lot of own devices where we try to create the necessary hardware we need in order to collect the data we need for our processes. Here you can see a helmet that is where we mix more or less HoloLens glass, which is, let's say, this data glass allows you to project pseudo-holographic visualizations in the environment. And this works actually indoors. What we managed to do is, by combining a GNSS antenna and some very nice transformational algorithms, to bring this outdoors. More or less, we managed to come up last year with Geographic-Aware AR. What does it mean? If you have any 3D model with a real coordinate, you can load it in our system, and when you go to this specific geographic coordinate, you will see this there, very highly accurately positioned in space. Why do we need that? Of course, because by that we can better control our other experiments. We can change the infrastructure, we can play with the infrastructure and collect data for our experiments. Another source of our data, we call it UrbanCore. We work with many partners for this. It's more or less a framework for retrieving preprocessed, or mostly preprocessed geographic data. VGI data, so voluntary geographic information from OpenStreetMaps. On the bottom of this slide, you can find a framework that we developed in collaboration with the ETH, my former group, where we did this framework where you can more or less simply, by choosing an area, download some information like number of type of intersections for this polygon, number and type of all possible combinations of the consecutive intersections. So more or less for this polygon, how many segments exist? That you have a three-way intersection in the first edge on the first node, and a three-way at the end. Four-way to three-way, three-way to five-way, and so on. Information about all three segments, anything you can imagine, the slope, the direction, the length, semantic annotations. So what are the surroundings? And we are implementing now in the last couple of months with a bunch of developers and students an API, so that we make it publicly available, so you can download the data, pre-processed data for the whole planet, fuse it for point. Fuse it for point means what can I see from a specific location? It's a polygon you get as a result. Street segment information, intersection information, turning angles, advanced visibility, so more or less advanced visibility is what can I see, or for a specific element, when can I see it when I'm walking on a specific segment? So more or less something like an isogist. Area type, more or less, is this an urban area, is this a green area, and so on. And then hotspot analysis, auto correlation you can do with this data. And of course, because we want this data to be really efficient in the pipeline of machine learning, we provide some data segmentation methods. Many more will come. We can do VGI data. VGI data, you cannot assume that they are correctly mapped. And there are many, many problems with this data because you have many holes, you have many wrong annotations or tags, and we have to find a way to clear them a bit, or at least validate them in order to know, okay, what percentage of my data is good to go. Here an example. So for an area that you're interested, let's say for coffee places, these are the blue points on the left side, our algorithm. So we would get as a result the chunks so we would like to have 5 chunks. We would like to split this area in 5 parts, where the number of coffee places is equally, you would get this as a result on the right side. Then the data segmentation as a polygon, where the areas are of equal length. This could be interesting for traffic forecasting, for example. There's also the function of turning angle. So you will see if you specify a specific route in our framework from 1, 2, 3, 4, you could more or less get all the angles of the whenever you change direction. I mean, a right here direction of walk, it could be also direction of driving, but you get the idea. And then we have the viewshed on the left side. More or less, it's a not the valid viewshed, but from the principle, it's the same. From a given location, which are the buildings that you can see? And on the right side, you have the actual viewshed, more or less a polygon that describes to the area with the given input parameters that is visible. So you can use this polygon created on the second image on the right, and query again the database and get all the data you need inside of this polygon. And then you would know, okay, all these elements, I can see them, or the user can see them. Why is this data framework relevant for us or for LBS? Of course, to inform the LBS, to use the characteristics of the environment for predictions, adapt based on the characteristics of the environment, optimize the content, and interaction dialogues. With this data that I showed you right now, we can select the proper environment for the experiment. So when we collect data, of course, you have to be somehow sure, or at least have some confidence that the selected experimental area is representative. So what we have done, what I'm not showing you here, is we have a framework where, based on the data I showed you from the UrbanCore, you can calculate for a given area all the possible routes of a given length. And then based on Z-score transformation and all that, you can get more or less a list of the routes, so a listing of the routes, a ranking, based on the average route of this area, based on the Z-scores we compute. And of course, based on several criteria, like length, like slope, like segment length, like turning angles and all this. And based on that, for a given area, we can say, okay, now we selected more or less representative area or representative route. And of course, when we know the environment, with this data you can download from our server, you can get an idea of the environment, of the urban characteristics. It's urban computing, more or less, what we're doing, and by this you can create virtual environments that resemble more or less a real environment. And by doing different changes, you can apply, you can perform experiments and collect even more data by slightly changing the setup and seeing in order to find out what is the effect if I change this or this. And I will close very soon, but before closing, I will tell you what is the problem we have often. We have the feeling that the architecture we have, the general models, they're not really capturing space or the geospatial characteristic of a given environment. We often say in our domain, that spatial data are special. Is that really the case? We have to figure out. Just to give you an idea, what are spatial data? We have raster data that save data in pixels, like satellite images, classified images, and then we have vector data, street network, building polygons. And what you see here is, on the right side, is a mix of these two data types, right? You have the image on the bottom, and the vector data on the top. And the question is, there is no unified model to combine both and how to integrate it into machine learning in a proper architecture, let's say, right? So there are questions like, through the aggregations we go through an architecture, we lose a lot of information, a lot of spatial information, and that's where we are looking at. That's where we are focusing at the moment. We try to see, first of all, if it makes sense to go towards geographic-aware machine learning, so to have a, let's say, awareness of the spatial characteristics of an environment, the relationships between the elements. That makes sense. Do we really need it? We are not sure. We are not sure yet. We are investigating exactly this at the moment to see if it's necessary to change the architecture, or we can go a step behind that and find better segmentation methods and better feature extraction processes. What we found out during this investigation was that the importance of geospatial semantics. We were surprised that what we can do by simply using semantics. Just to give you a spatial introduction, a geo object has a semantic value and a location. As you can see here on the right side, we have a polygon. This is, and the semantic value is Stephansdom, and this is a historic thing. If you go with ontology of the OVL, this can be a historic thing, this can be a historic building, amenity, and so forth, right? And by looking at this, one of my PhD students, Martin McCutcheon, focused on land cover classification and urban growth. Simply by using the semantics, he managed to beat more or less the image-based classification for land cover and urban growth. And this is a good indicator of how important, or what we can do, or what we are still missing by looking on, or without integrating the spatial data we have available. For example, the VGIS semantics that you can download from OpenStreetMaps. And one of the very interesting topics we have at the moment, where a student of mine is working on with Marvin, is to work on synthetic data by training again. The input is exactly the semantics I was mentioning, and certain remote sense images trained again, and then the scan is able to synthesize the data we need. And this data is going again back to our initial model and train it even better. So we created this closed loop, and it looks like this is still work in progress, but looks very good, very promising. What you can see here on the images, the top rows are always the real data sets, examples of real data sets, and the bottom rows are examples of trained data sets. You can see there is still work necessary there, but it already starts looking good. And from the results, we get something. We are not still there. So I will close my talk with this, with the main problem we have. So should we go towards spatially aware, or just spatial aware machine learning or not? And I hope you got something from my talk. Thank you very much.
Firstly, again, thank you so much for your brilliant and all-encompassing talk, really. You must have a group of 300 people working on all this. I was wondering, you have all these amazing systems for collecting data at many levels, you know, the position, the eye gaze, everything. And I suspect that technology evolves very fast there. And I was just wondering, how do you deal with that? Are your models sensitive to the actual nature of the data? I mean, if you change from one eye gaze tracker to the next, can your models continue? Or, I mean, do you do end-to-end training and somehow decouple the signal layer from the rest? Or do you break down the complexity by having modules along the route? Maybe, I don't know whether it's clear where I'm heading, but maybe you can comment a bit.
I think I get to the point. So indeed, what changed, especially in the eye tracking domain, is in the past, when you would do outdoor experiments with an eye tracker, we get an accuracy of about 5, 6, 7, 8 degrees, and now you get down to 1 degree, which is a huge improvement. I would assume that the models should get better, but to be honest, we never try that. To be honest, once we close one problem, we start with the next one and don't look back.
Okay.
We should do that.
So when you move on to new technology, you start asking new questions. So it's hard to say how the models respond to the actual structure in the data.
Not really. So we still use eye tracking to answer our questions, but the problem is, in order to find out what you ask for, it's more or less a sensitivity analysis. I take the same model and run it with the new data and see how it behaves, because now the model, you don't know where the effect is coming from. It can come from the model or the data itself. So if we fixed one problem, or if we show that it's feasible, then we don't really only rely on the data, but we try to optimize the model. So we don't do this type of sensitivity analysis, but it sounds like a good idea to at least take a look on the effect. But I would guess that it should get better.
Okay.
Because you have less ambiguities, right?
Okay. Or perhaps similar, you mentioned this interesting work on going from semantics to land use classification. If you pick the different source, would this work equally well? I mean, do you know how sensitive the approach is to the nature of the input data?
Not really. So what we do now is we take random samples from around the planet. I think Europe was our area. So we take random cells. So we have a raster with cells of, I don't remember, I think 1 kilometer to 1 kilometer. Or, no, sorry. I think for the Lanka we was 20 by 20 meters, if I'm having in mind. And we were taking random samples around Europe to see that, how it works. That's the only sensitivity analysis we have done there. Now we are focusing on experiments because we are also working on site, actually with you, where you try to understand why it's working so good. And the good thing, what I didn't tell about semantics is, when you look on the area of towards explainable AI, for example, what we did is, or what Marvin actually did is, he applied visual saliency maps, in order to figure out the importance of every specific semantic word or specific word that we had in our classification. And the good thing about the semantics is they're explained by themselves, right? You have the words that you can use. And what we are doing now there is more or less we are running this visual clusters on different areas in order to see if it stays or remains stable. We don't know it yet. It's still on work in progress. So we are doing it actually quite now.
So I was wondering, you mentioned these different sources of information. You have the semantics. You mentioned image data both from the satellite, and you also said you're looking into using image data from Familiarity, say. So these are completely different types of sources of information. How do you intend to combine them? What is your approach? Do you have multiple ideas, or do you have something where you already know that will work because you've used it in the past? This seems to be a really challenging and interesting area from my view.
At the moment, we don't try to combine this. Right? So as I told you at the beginning, we focus on the environmental context separately first, user context separately, and then the technological context. So then with mapillary data, based on, I didn't know this actually, this framework and the abilities of this. Thank you very much for introducing me to that. We try to solve one problem. With the satellite images or the semantics, we try to solve a different problem. So we have different models that work all together but separately to inform the AI under the hood. So the one model tells the AI, okay, this is this type of area. The other model tells the AI, this is more or less this type of action that is required, and so on. We don't have yet a model to combine all this. And the biggest challenge is, if you have raster data and vector data, so there are no real models for vector data, right? So how to integrate vector data from machine learning purposes, and there is no unified model to combine raster and vector data meaningfully. So you always lose information, and that's the point. This is more or less the common problem that all our models have. How can we close this gap? How can we stop losing the information for vector data by rasterizing them?
Yeah. Well, that's why I was kind of curious. You know, there are graph-based models, but how do you combine these very different types of resources? It's really exciting research. Thank you so much again for the presentation. I guess all the other listeners are just bowled over by this sci-fi work that you're doing. Thank you again so much, and I hope to see you soon in Vienna.
Thank you.
Thank you, Ioannis.
Bye-bye.